Hello everyone, I welcome you all to the course UAV design. Today we are going to discuss about fuselage lofting and techniques for shaping fuselage contours. The fuselage of an unmanned aerial system is indeed a critical component which goes beyond mere structural enclosure. It directly impacts aerodynamics, payload integration, structural efficiency, and operational versatility. Breaking down these key considerations, design techniques, and configurations in unmanned aerial system fuselage design begins with the very first parameter is key design drivers for unmanned aerial system fuselages. Here, the major one is the payload accommodation. Unlike manned aircraft, UAV fuselages prioritize sensors, cameras, batteries, or cargo space over human ergonomics. The shape must protect payloads while allowing optimal functionality. Example, unobstructed camera views. Whenever we are placing the camera beneath the unmanned air vehicle, suppose this is my front view, if I'm seeing it here, it shouldn't affect the design and contour of the fuselage at this part. The key design drivers for unmanned air vehicle fuselages are aerodynamic efficiency, which ensures minimizing the drag because drag is a crucial for endurance and speed. This often leads to streamlined, slender designs for high altitude, long endurance unmanned air vehicles or blended bodies for stealth. Structural weight is one of the parameters where composite materials like carbon fiber, Kevlar are common to balance strength and weight, especially for small unmanned air vehicles where weight savings directly impact flight time. Stealth and low observability. Military unmanned air vehicles, example RQ-170 Sentinel, which is used face designs and radar absorbent materials to reduce detectability. Modularity. Some unmanned air vehicles feature swappable payload sections or detachable fuselage modules for rapid mission reconfiguration. Fuselage design techniques. The very first one is aerodynamic shaping and streamlining. We use computational fluid dynamics to optimize cross-sectional area distribution. For example, Sears hack body for low wave drag in high-speed unmanned air vehicles. We use the technique of blended wing body, which is commonly used in unmanned air vehicles. For example, X-47B, where the fuselage merges with the wings to reduce drag and increase lift efficiency. It looks like this. If this area is a fuselage and this is the wing, which is incorporated. Then flat bottom designs. For low altitude unmanned air vehicles, a flat underside can improve stability in ground effect or simplify sensor mounting. Structural design. We have two types of configurations for the fuselage structure. The first one is monocoque and the second one is semi-monocoque. So depending upon the unmanned air vehicle mission, we choose whether a monocoque or semi-monocoque. Some small unmanned air vehicles often use monocoque, that is single shell structures for lightweight, while larger ones employ semi-monocoque because it includes frames, and on the frames we'll have skin for rigidity. 3D printing. Additive manufacturing allows complex, lightweight geometries for customizing unmanned air vehicle fuselages. Example is lattice structures. Direct HTML file can be printed as a component there, and it is reassembled and then it is tested for flying. Thermal and EMI management ventilation. Electric unmanned air vehicles require cooling for batteries and motors. Openings must be aerodynamically optimized. EMI shielding is critical for intelligence, surveillance, and reconnaissance. UAVs to prevent sensor interference. Design steps for unmanned aerial system fuselages. The first one is mission requirement analysis. First, we define payload size, endurance, speed, and operational environment. Example, maritime unmanned air vehicles need corrosion resistance. The second one is conceptual layout. Deciding on the fuselage configuration, cylindrical, rectangular, or blended. Depending upon the configuration which is required, we choose that and integrate it with wings and empennage. CFD and wind tunnel testing. We validate drag and stability characteristics during these tests, and structural finite element analysis is done to ensure the design withstands flight loads, for example, gust loads and landing impacts. Payload integration. It ensures sensors, communications have clear line of sight and minimal vibration. Prototyping and iteration. Rapid prototyping, example 3D printed scale to find fit and function, we use it. The common fuselage configurations, which we generally find in most of the unmanned air vehicles, depending upon the mission requirement analysis. First, we define payload, size, endurance, speed, and operational environment. Right? And depending upon the mission, we choose our configurations. For cylindrical type of configurations, we use for long endurance and high altitude long endurance unmanned air vehicles. For example, Global Hawk. This is an existing unmanned air vehicle. We have rectangular box configuration for small quadcopters or fixed wing unmanned air vehicles, and DJI matrix is a payload section here. Then we have configuration blended wing body, which is used for stealth unmanned air vehicles or combat unmanned air vehicles. The existing unmanned air vehicles are X-47B, BAE, Taranis. Then we have flat plate configuration, which is low cost reconnaissance, and existing unmanned air vehicle is RQ-11 Raven. Then we have multi-boom unmanned air vehicle configuration, which has a separate payload from propulsion. For example, MQ-9 Reaper is an existing unmanned air vehicle in this category. Lofting. Lofting is a precise process of determining the external geometry of a vehicle, and in our case, the unmanned air vehicle fuselage. It's essentially sculpting the outer shape to achieve optimal performance. The contour of the fuselage will be designed using lofting technique. Lofting is a fundamental technique in aerospace design that defines the smooth, aerodynamically efficient external contours of an unmanned aerial vehicle fuselage. It bridges the gap between conceptual sketches and manufacturable geometry, ensuring that transition between cross sections is seamless and aerodynamically optimal. The primary objective of this lofting is to minimize fuselage drag while potentially producing a fair amount of lift. During the lofting process, designers aim for a smooth external shape by carefully designing cross-sectional areas along the length of the fuselage to minimize any sharp edges. Sharp changes in shape are particularly problematic at junctions like the wing fuselage, tail fuselage, and engine pylon fuselage interfaces, where flow separation and turbulence can occur, increasing drag. Filleting, which involves adding smooth transitions, is crucial here. Filleting is if this is a structure where two geometries are joined, we'll give one fillet like this, ensuring that it is streamlined, and whatever air is there, it will pass like this over it. Aerodynamic efficiency in unmanned air vehicles depends heavily on smooth external contours, and gradual transitions between fuselage sections. Poorly lofted shapes lead to flow separation, increased drag, and reduced endurance, which are critical issues for fuel or battery constrained unmanned air vehicles. Principles of streamlined lofting. First one is cross-sectional area distribution. We follow the Sears Hack body or von Karman ogive for low wave drag, which are critical for high-speed unmanned air vehicles. It ensures gradual expansion and contraction by avoiding abrupt changes in diameter. And the third category in this which we follow is use of area ruling, that is Whitcomb's rule, to smooth out transonic drag rise. One example for this area ruling is Coke bottle shape, which was a reference for designing a transonic aircraft. Then continuity requirements. G0, that represents the position continuity where there are no gaps between the surfaces. Then G1 is tangent continuity, which is a smooth transition ensuring that there are no sharp edges. Then we have G2, which is curvature continuity, which is optimal for aerodynamics. Example, we can see in luxury cars and high-end unmanned air vehicles. Critical junctions requiring special attention. Wing fuselage, wherever the wing fuselage both are integrated, there the problem is flow separation and induced drag, and which can be uh, solved using fillet blending. And then at tail fuselage, the integration of tail with the fuselage, which raises to a problem, turbulence affecting the empennage, which can be sorted using tapered booms. Then engine and pylon fuselage, where engine is integrated on the fuselage or on the wing. We have a pylon system there on which the engine is podded. It leads to interference drag and it may also lead to vibrations. So this can be controlled using nacelle fairings. Then when we mount sensor or camera houses, it disrupts the laminar flow. So in order to minimize this disruption, we use dome blending. Techniques for smoothing transitions. First one is filleting and blending. Fillets are rounded transitions at junctions, for example, at wing roots, to prevent vortices. Blending, it's merging surfaces smoothly, ensuring like it's blended wing body unmanned air vehicles like X-47B. Guide curves, which is used in CAD tool to control lofting parts. CAD tools, for example, Rhino, CATIA, and nowadays people also using SolidWorks. Next, computational fairing, which is surface optimization. We have here curvature comb analysis, which detects surface irregularities. CFD driven refinement, it adjusts lofting based or on pressure distribution. Then we have Class A surfacing, which is high-end automotive aerospace technique for ultra-smooth surfaces. To reduce drag significantly, the fuselage cross-section should resemble an airfoil shape from the side view. This often involves adding a semicircle to the nose and applying a cone to the rear fuselage. For subsonic aircraft, the taper angle of the rear fuselage should generally not exceed about 20 degrees to avoid flow separation. For ease of fabrication, parts of the rear fuselage might even be conical with smooth transitions from cylindrical sections. To prevent any unwanted yawing movement caused by the fuselage itself, the top view of the fuselage is recommended to follow a symmetrical airfoil shape. Side view fuselage shaping, aerofoil inspired fuselage design, ensuring that semicircular or elliptical shape or low pressure drag or smooth airflow transition is been incorporated. Example, Global Hawk's nose for laminar flow. Rear fuselage, gradual taper less than or equal to 20 degrees semi-angle to prevent flow separation. Conical or slightly curved for easier manufacturing. Example, Predators unmanned air vehicles, tapered tail cone. Avoiding flow separation in the aft body. In subsonic unmanned air vehicles, taper angle less than or equal to 20 degrees, empirically derived to delay separation. Too steep, turbulences increase drag. Example, early drone prototypes with abrupt truncation. Supersonic unmanned air vehicles will have sharper taper. Example, Lockheed D-21 drone to minimize shock drag. Top view fuselage shaping. Why symmetry matters in fuselage designing? Because it prevents yaw instability. Because asymmetric fuselage induces unwanted side forces. It mimics symmetrical airfoil, which is neutral aerodynamic behavior. The flow will be neutral on the either sides of the fuselage. And why we recommend top view profile in this case is elliptical or symmetrical NACA like shape. Example, RQ7 shadows fuselage will avoid flat-sided box designs unless required for payload. It increases from drag. Exceptions for special cases. Stealth UAVs use phased but balanced designs, and high-speed drones may have slight asymmetry for propulsion integration. Real-world unmanned air vehicle examples. RQ4 Global Hawk. The fuselage cross-section here is like airfoil from the side profile and it has conical tail. MQ9 Reaper is having symmetrical top view and cylindrical midsection. DJI Matrix 300 had flat-sided for payload but rounded edges. X-47B unmanned air vehicle has blended wing body with no distinct fuselage. The impact on communication system. Lofting also plays a role in optimizing the environment for communication systems. For example, the distinctive bulge on the top of the Global Hawk's front fuselage houses a 48-inch wideband satellite communications antenna. The radome covering this antenna must be designed with a specific curvature and metal properties to allow signals to pass through without distortion or degradation. Verification of lofted fuselage aerodynamics, wind tunnel testing, and computational validation. The lofting process defines a unmanned air vehicle's ideal aerodynamic shape, but real-world performance must be verified through wind tunnel testing and computational validation. Both the results has to be compared, and the experimental versus computational, how much the results are matching, that has to be cross verified in percentages. These steps ensures the design fuselage meets expected lift, drag stability, and communication performance metrics before manufacturing. Why verification is critical? CFD has limitations for turbulence modeling, transition prediction. Unexpected flow separation may occur due to minor surface imperfections. Antenna radomes and payload bulges can disrupt airflows in ways simulations may miss. Pitching yawing movements must be measured for flight safety. Wind tunnel testing for lofted fuselages. The parameters on which we do the wind tunnel testing is, the first one is drag coefficient, verifying if lofting achieved predicted and the drag reduction. Lift distribution parameters tested for unindented fuselage. Lift affecting wing aerodynamics. Pitching moment, it ensures fuselage does not introduce instability. We have flow separation. where we identify the stall inducing transitions, ensuring that there is no early stalls here. Then radome effects, test if antenna fairings cause turbulence or buffeting. Testing methods we have for wind tunnel. The first one is force balance measurement, where we measure lift, drag, and moment coefficients directly. Examples we like NASA's Langley subsonic tunnels, where Global Hawk validation was done. Then we have flow visualization technique, where smoke or tuft testing reveals the separation points. There we can trace out where the flow is getting separated. Depending upon the analysis and the results, if it is needed, we can modify the airfoil or the wing structure to ensure that there is delay in the stall. Then oil flow patterns, how surface have the streamlined flows. Then PSP test, it detects local pressure variations which validates CFD predictions. Then aeroacoustic testing, it checks if radome causes any noise which is critical for stealth unmanned air vehicles. Computational validations, while wind tunnels testings are the gold standard, CFD supplements testing by identifying problem areas before physical testing, optimizing lofting testings, fillet ready, taper angles, etc., simulating different flight conditions at high altitude and crosswinds. And the CFD best practices for loft verification is mesh refinement near critical zones such as wing fuselage integrations and radomes. Then transition models where laminar turbulent shift is being tested. Then RANS versus LES, where RANS for initial screening and LES for detailed separation analysis is been done in CFD tool. Coming to the conclusion of this lecture, the fuselage lofting should have aerodynamic efficiency, which ensures the fuselage shape directly impacts drag and flight endurance, requiring both smooth contours and optimized cross sections for minimal resistance. Payload centric design, unlike manned aircraft, UAV fuselages prioritize sensor, battery, and cargo integration, often sacrificing crew space for mission specific functionality. Structural optimization, it's an advanced materials like carbon fiber composites, reducing weight while maintaining strength, which is crucial for long endurance or high agility unmanned air vehicle systems. Mission driven configurations, fuselage designs vary widely from cylindrical bodies for high altitude long endurance drones to blended wing body layouts for stealth and efficiency. Verification is critical. Wind tunnel testing and CFD validate lofted shapes, ensuring aerodynamic performance which matches theoretical predictions before manufacturing. The future focus is AI driven design, morphing structures, and smarter material use will further enhance fuselage capabilities. These are the references used for this lecture. Thank you. We'll meet in the next lecture.